Of redoing everything, I'll just do it in one example. And we're going to see what it means to vary stability in this example. We're not going to use so much about moduli spaces of complexes, but just of sheaves. And so I'm going to explain also the lemma that we saw today that was a bit confusing. And I'm going to apply also Abramovich-Polishuk at a certain moment, which is also was confusing, but hopefully now it will become a bit better. So we start again with x as surface. So we are as today as before. So let me assume something, just for simplicity. They're not important, but let me assume the following two things holds. Just to have some, at least notation is easy. Let me assume that the regularity is 0. Okay, so h01 is 0. And let me assume also the Ronse vary of x is just one dimensional. And just to fix notation, let me say that h squared is equal to d. Okay, so that's our, and this is an ample generator. Okay, so it's a very particular case of what we were seeing before, but it's fine. So that's the. So what I want to do? I want to apply all the thing we saw before to study one particular moduli space, just one, which is the Hilbert scheme. So I'm looking at xn, which is the Hilbert scheme of dimension 0 and the length equal to n subschemes. Okay, so a generic point is n distinct point on the surface, especially just some zero-dimensional subscheme supported somewhere. Okay, so I think it has a Hilbert scheme, but here I'm looking at sheaves, so I'm thinking to it as the following. So this is the moduli space of semi-stable sheaves, but in this case there will be all semi-stables of ideal sheaves. I of gamma, where gamma is as before, so it's length of gamma equal to n. Okay, these two are equal, and they are both smooth, so this is a smooth variety. It's projective, and this is integral, so everything is nice here. Okay, so that's my moduli space, and with respect to the notation of today, the vector I'm taking is the following. So they have rank 1. I don't need to worry about fixing the determinant because this guy is 0, so there is nothing to fix. So it's just taking 0, and then I want the length. So the second chair character is going to be minus n. Okay, so those are the moduli space I'm looking at. And so in the notation as before, I'm looking at, so the game I'm playing is I take omega as alpha times h, I take b as beta times h, so that's my alpha beta plane. Here I don't have any choice, but still it's something. And yeah, I'm looking at the moduli space of sigma alpha beta with vector v0. Okay, so that's what I want to look at. I don't care so much about, in this example I'm going to discuss, I don't care so much about everything, but I'll show you a bit later what happens for K3 surfaces, and then I have to care also about complexes. But here, not too much, actually. And so let me state a small result. Fact. I'll tell you in a second how to show this thing. So there are only two divisor classes on the model on the Hilbert scheme, and these are the following. So this is the fact. So the Ronse vary of the Hilbert scheme is generated by two divisor classes. One is I call it B, and one I call it H, which by abuser notation is the same H as before because of course they are related. Okay, so let me explain how they come from. So the Hilbert scheme. Oh, B is bad notation. Ah, yeah. Okay. D. Oh, D is not so. Delta. Delta. Oh, delta is bad. C, D. Let's say D. D is fine. I hope it's fine, D. Actually, let me call it as it should be called. So it's E divided by 2. Okay. That's a better notation. Okay. Okay, now I have to not get confused. So what is E divided by 2? It's E divided by 2, as you can imagine. So it's just, so I take the Hilbert scheme, and I can look at the map forgetting the scheme structure on the points, but remembering just the multiplicity. And so this guy is going to go into symmetric product modulo the symmetric group sigma n. And this is singular. It is well known that we saw maybe already. So this is the Hilbert to Chow morphism, and this is well known as a Crepant resolution of singularities. And so what I can do now, so this is a Crepant resolution. There is an exceptional locus, which is a divisor, which gets contracted. And so this is my exceptional divisor E. So the interesting thing about the Hilbert scheme is that E is integral, but is actually divisible by 2. Okay, and there is not so nice description about it because this guy is not going to be effective. And what is H? H is the following thing. H, I take the divisor H on X. I take the product n times, and then this guy is invariant under the direction of sigma n, so it descends here. And then I just pull it back. Okay, so let me just denote this guy by the symmetric product, and then I pull it back. So by abuse of notation, this guy actually should be called as HC star of Hn. But I just shortened notation to H. Anyway, there is not so much confusion, hopefully. Okay, so this guy is semi-ample, very nicely, and this guy is an effective divisor. Okay, so the question that we are interested in is very simple, is what is the net con? And maybe I can say more, maybe I can run the whole MMP for this kind of spaces, and I can do it maybe by varying stability. And the interesting thing is that this is actually true, but only in some examples, like P2 or K3 or abelian surfaces. But at the moment, it's a general thing, so let me just show you that by varying stability, I can describe a piece of it at least. And sometimes I can actually describe it all. Okay? So let me maybe, and it's interesting that the divisors here, which are ample, are well studied are studied in the literature, but by giving some certain mapping to Grassmannians. But those are not enough. You will see from the theorem, you will get more than what was known before, just by doing some simple computation in this space. Okay, so let me say one more thing about this thing. So how do I think about these divisors? So the way to think about them is to think, instead of thinking inside of Xn, I'm thinking inside the cohomology of X. And so how do I do this? As the following thing. So I consider the following map, lambda from K0 of X, okay, that we already introduced, the Grothendieck group. Maybe let me put an R here, although it's not really necessary. And then I'm going into N1 of Xn. So this is, oh, sorry, I did not before NS. Okay. And what is this map? So this map factors VHCH. Let me just write it briefly what this map is. And so this map lambda, how is defined this map lambda? Lambda is defined as follows. I'm just taking a class, and I do the following operation. I take the pullback. Sorry, let me just introduce some notation more. So I have Xn cross X. I have the two projection onto X and Xn. So this I call it P, this I call it Q. And this side I have my Xc, which is my universal family. So this is a universal family of sub-objects consisting of blah. So what I do, I just take the pullback of W. W is here. I pull it back to the product. I smash it with the class of the ideal sheaf of Xc. Okay, and then I push it forward on K theory onto Xn, and then I take the determinant. Okay, this is a standard construction of determinant bundles. Okay, and the interesting thing is that this map is actually an isomorphism from some subspace of here inside the Néron-Severi, and I can show you actually, instead of telling how it works, I'm just telling you what is the W that gives you these two divisors. The lambda of 0, okay, I have to be careful with the signs here, minus mh, and here you can put whatever you want. So this guy is going to be mh, with this, hopefully the signs are correct. And the lambda of the vectors of the form 1, 0, and here I can put whatever I want, is going to be my B. Oh, sorry, my E divided by 2. Okay, so that's just a map. Okay, and the push forward in K-theory, maybe I didn't define before, but that is what you might imagine it is. So the push forward in K-theory is just taking the alternating sum of the Ri push forward, and then extend by linearity. Okay, so that's that's the picture. And so what is the theorem? What is the proposition you can prove is the following. So let me state it. I'll give you some examples, and then we try to prove it. So proposition. This actually was later generalized to a nice paper by a lot of people. But so let me say like this. So the first thing that I can say is the following divisor is nef. So minus E divided by 2, that is an ugly formula, plus D plus 2n divided by 2D times H plus Kx divided by 2. I'll tell you in a second what it means. So this guy is nef, the Hilbert scheme. So what is Kx? Kx is the same thing. I'm just coherent with my notation. I take the canonical on X, I pull it back to the symmetric product, and then pull it back to the Hilbert scheme. Okay? So that's the first statement. And the second statement is that I can also tell you when this guy is going to be the boundary of the nef cone. So if there exists a curve in the linear system of H, and there exists a G1n on C, then it is not ample. And the interesting thing is that you can use stability actually to also say vice versa when there is a G1n. But anyway, but only in some cases, for example, in K3 surfaces. Okay, so that's the theorem. And the corollary is telling the following thing, that I know at least a region in the nef cone, and if I'm lucky, I also know the whole thing. I'll show you an example in a second. But corollary, it says that if I take this monster, then the nef cone of the Hilbert scheme, it contains the cone generated by H and by this guy here. Okay, so that's the theorem. Okay, that's the result. So I want to prove it. Okay, so how will I prove that this guy is nef? By using stability. Okay, so let me just first give you an example before going to proof. Two examples. So one is easy. If you take P2, okay, so that is well-known result. If you just plug the constant, it's actually telling you that so in this case D equal to 1. H is just a J1 on the line. C in this case is just a line. So I know there is a G1n. And so what it means that minus B plus, come on, I'm not too used to call it B, plus n minus 1 H, it's in the boundary of the nef cone. Okay, so that's the description of the nef cone. This was well-known result by many people, Beltrametti, Sommese, Goetze, Catanese, Goetze, or Li, Qing, and Zhang. And but you can recover it in this sense. But that's not so. That's one thing. But that can be done also by standard method. So that's nothing so new. But if you start with the next example, which is slightly non-trivial, you get already something new, which is the K3 surface case. So if I take X a K3 surface, so K3 surface means that canonical is trivial and is simply connected. Then, and I'm assuming that n is greater or equal than D plus 6 divided by 4, something like this. I'll tell you later why this thing happens. And then again, somehow this number is exactly the number that you know by Lazarsfeld, or anyway, by some, that there is a G1n on your linear system. And so what it means I found the boundary. Okay, so again, and the divisor is minus B plus D plus 2n divided by 2dH. Is in the boundary of the nef cone, of the Hilbert scheme. Minus E, thanks. 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 All right, so this is already something newer because of this 2D actually. So all divisors you can get classically by k-ample line bundles. They're going to have only 2 here. So this you get something newer in this way. And also actually, okay, for this was the first example we had that with Arend. Actually, everything that I stock here is with Arend Bayer. I will tell it later. But this was one of the first examples we had that somehow contradicts some conjecture by Hasse-Schinkel, which then we fixed on the K3 surface case. But anyway, okay, so good. So that's the statement. Those are 2 examples. So how do you prove this statement? And so let's see. So the first thing I have to do is just to take the Hilbert stem. I know that for alpha large is going to be just my moduli space, and then I start moving stability. And when I hit a wall, I'm going to hit something which is Neff in the boundary somehow. So what I'm looking at again at my space of stability conditions. So this is beta and this is alpha. Okay. So that, as we said today, so I have to look at where ideal sheaves are in the category. And so I'm looking at ideal sheaf of gammas, okay, where gamma equal to n. So when are they in the category? So these are slope 0, so I have to choose beta to be smaller than 0. So I'm canceling this part, and so I'm looking somewhere here. And so somewhere here, for alpha large, the moduli space is going to be the Hilbert scheme. Okay, so that's the lemma that we said today. So for alpha large, is the moduli space is just the moduli space of Gieseker stable objects with the fixed vector. In this case, it's just a Hilbert scheme. Okay, so now what we're going to do this following trick. So let me prove maybe this result that the following is true. Now I want to know when they are stable. Okay, and so that's the following lemma, which said the following thing. So I'm taking an object E in my category co. Now H is fixed and it's unique, so this category depends really only on beta. And so such that the Chern character of E is the Chern character of the ideal sheaf gamma. So it's, as I told you before, is 1, 0, negative n. Okay, so an object which has this character, which is in the category. Okay, now I choose beta to be in the following region in between -1 and 0. So that's a very easy computation. Let's see. You'll see how easy it is to deduce this result. Then the following thing is true. So this is more precise than the lemma we saw before. So this is telling you the following thing, that E is sigma alpha beta semi-stable if and only if it is stable. If and only if it is an ideal sheaf of gamma. Okay. So in this region that I'm putting here, I know that is the Hilbert scheme. Okay. So it's a bit more precise than the lemma before, right? Now I really tell you exactly. So I know that for alpha large is true. Now I'm telling you, okay, in this whole region there is nothing. So it's just Hilbert scheme. Okay, so how to prove it? Let me prove it. It's very elementary, this thing. It's just really elementary arithmetic. So how do I do that? Oh, sorry, let me say one thing. So now the next thing I'm going to do is I'm going to associate a divisor to this thing. And if you know exactly when the last wall is, you get exactly the Neff cone. So that's the philosophy. Okay, so proof. Okay, the first thing I have to tell you about walls. So what are walls? We already said what are walls. So walls is where I have an object which is semi-stable on one side, and it crosses the wall and becomes unstable. Okay, so that's what a wall is. And so what I'm doing, I'm fixing my V0 as before. And then what are the walls? The walls are actually very simple. Can only be of 2 types in this coordinate system. If you change the coordinate system, they're all the same way. But anyway, so the walls are actually, they can only be vertical line and only one, and I will tell you what it is and what it corresponds. And the others are semicircles, you probably saw this picture, which are nested, and they're converging to a certain point, which I will call it beta bar. Okay, so what it means, this picture, it means the following, that if I have, so these are nested semicircle. Which, whose centers converge to beta bar such that, it's actually very simple, the CH2 of beta bar of my vector V0 is equal to 0. So it's the point when the CH2 is going to be 0. And as I told you before today, I will not have time to explain, but the more you go toward this point, the more geometry you get. So some of the idea is that if you go alpha large, you get usual stability. If you go alpha low, small, and nearby this point, you get all these interesting things. So that's what we want to do. And OK, so now the following properties. The walls, they accumulate near this point. At this point, you can compute very easily. It's above -1. So the walls do not intersect. So the only thing I have to prove is that for beta equal to -1, there is nothing. OK. So they do not intersect, they are nested. Okay, so that's the easy part here. So walls are nested. It implies I can take, which is actually fine for what we need, beta equal to -1, and prove that there I have no wall that intersects this thing. And so how does it go? Well, let's prove it, that there is no wall. So we saw one trick to prove something is stable, which is by using that the Q is minimal. Now I'm going to use another trick, which is to use that the rank is minimal. But the new rank now. So let's check.
You couldn't have walls that would be entirely containing the strip.
Yeah, sorry, because, I'm sorry. And beta bar, if you compute beta bar is smaller or equal than 1. So -1. Thanks. So no, right? Because they're all oh yeah. Thanks. Okay, so actually let me say also one thing that I forgot. The walls are finite outside this thing, but they might be infinite when I go nearby beta bar. Okay, and actually they are infinite. Okay, so how do I prove that the ideal sheaf is stable or something is stable? So there are two things to check. But the first thing I want to do is compute so recall that we have our function z alpha beta. And up to rescaling, so this I write it at d alpha beta plus square root of -1 rank alpha beta. Okay. And so I look at the rank first. So in these constants, the rank is actually very simple. There is a constant alpha, which goes outside. And then I have times h times c1 beta. But beta is -1, so I can write explicitly what this guy is. So it's alpha times, and what do I have? I have just, I'm sorry, let me just do it. Let me write it. H times c1 plus h squared times the rank. Okay, so that's what we have here. And now there is a following thing. So I'm assuming that the Picard is 1. So I can write my vector, any vector, as rank c times h and some third-chain class s. And so this guy, what it is nothing but alpha h squared, which is d, times c plus r. Okay. Now what is the trick? The trick here is beta equal to -1. So the trick is the following. This is a constant. That, OK, I vary alpha, but still it's like a multiple of alpha. So they're all the same for every class. And this guy is an integer. Right? So this guy belongs to alpha h squared times z. And now what is the trick? The trick is that if I plug my vector 1, 0, minus something, this guy is going to be the minimal possible, which is non-zero. But if it's 0, it's something on the other side. So I'm just using this as a sort of stability. So let me just say here. Actually, so how does it go, this thing? It's so it's the following. So this, I also have that R alpha beta of my vector 1, 0, negative n is just equal to alpha h squared, which is the minimal possible except 0. And now I argue as follows. So there are so if I have a sequence like this, okay, so this is an exact sequence in co-beta equal to -1 of x. And let me assume that this guy in the middle as R alpha beta to be minimal, so to be alpha h squared. Now it's very easy because somehow this guy is positive on the whole category, right? So this guy is positive, is the minimal possible. So it means that either this guy is 0 or this guy is 0. Okay, so that's just by positivity, right? They are both positive, and this is the minimal one, so that's the only thing that can happen. And now what I want to prove, okay, so let's prove now this dilemma. So I want to prove the two implications. So let's check first that, remember which one is the easiest. They're both very easy, actually. So let me show first that sigma alpha beta semi-stable implies that is I gamma. Okay. So how do I prove this thing? Well, this is a standard thing, and this is actually the proof of the previous lemma. So I just prove it in this sense. So this is a complex a priori with two cohomologies, right? So I can consider the following short exact sequence. So I take cohomology of E, shifted by 1, goes into E, goes into H0 of E. So by definition, this is a triangle, but it's actually a short exact sequence in our category. Okay, so that's the trick. Beta equal to -1. Okay, and so how do I go from here? Well, it's actually somehow E semi-stable. So, and if I assume that H-1 of E is non-zero, then what I get? Well, I get the following thing, right? So this guy as rank positive. This guy is a shift by 1, so the only possibility that this guy is rank 0, so it's going to destabilize it. So let me write like this. So this implies that R of H0 of E is equal to 0. That's the only possibility I can have. Because if this has rank 0, this destabilizes. So it cannot be. So this guy has to have rank 0. And if this guy is rank 0, but is in H0, that's what we proved in the lemma a long time ago. H0 has to be torsion in dimension 0. This is what we proved really yesterday, essentially. Okay, so that's the trick. And then that's it. Because then I get a contradiction by saying that, I don't want to spend so much time on this thing, but it's now how do I get a contradiction? Because somehow now this guy is rank 1, this guy is negative rank. So this is rank 0. So this implies that the rank 1, which is equal to the rank of the actual rank of E, is equal to the rank of H-1 of E shifted by 1, which is negative. Okay, so that's a contradiction. So what I proved that if something is semi-stable with cohomology in degree -1, which is non-zero, there is a contradiction. So it means that h minus 1 is 0. Okay, and so it's a sheaf. So it's a sheaf with rank 1. So now it's not so hard to show that the same argument, implies that E is torsion-free. Because if it has torsion, then I argue as before. And so it's a torsion-free of rank 1. So it's an ideal sheaf. Okay, so that's the easy argument that we have here. So that's okay. Question about this part? I hope that it seems complicated, but it's actually very simple, this argument. It's just like I use this rank as a new rank, and then I just get a contradiction by looking at the old rank here. Okay, so far so good, right? And the vice versa is actually very, so this I prove that something has to be an ideal sheaf, but I use the same trick to prove also the converse. The converse is very simple. So vice versa, I want to prove that if E is an ideal sheaf, then E is stable. Stable. Okay, this will be enough, right, for proving everything. And so how do I prove this? Well, again, I apply the same trick, right? If something is destabilized, one of the two have to have rank 0, new rank 0. But somehow, this cannot have rank 0, so this has to be rank 0 if it's not stable. So, oh, sorry. No, but E, okay. So if I gamma is not stable, then there exists a sequence as before. With the only possibility is that the rank of this guy, the new rank, is equal to 0. But then I know how to control this object. These objects are the one that we checked for Bogomolov inequality, again, the same time. So this implies that A can only be at the following form, essentially. It's an extension of guys the following form, which could be only a sheaf shifted by 1 of something which is a skyscraper, or extension of them. Yeah, but this is a sheaf by 1, so there is no morphism into the ideal sheaf. So these are negative homes, so this is 0. And this guy is a skyscraper, and the home from a skyscraper in torsion-free is 0. Okay, so there is no possibility, and so that's it. Okay, so that's a proof. It's a proof essentially of the lemma. So I hope I show you in this example that I can explicitly say when this guy is stable. Okay, now, okay, so good. Okay, now the Neff line bundle. Also, how do I do now? I define the following thing. So here is the positivity. Sure.
Why torsion-free rank 1 is it going to give sheaf?
Yeah, because we are, Here we are assuming something, right? We are assuming that it's a regular. It's H1O is equal to 0. And then it has rank 1 and C1 equal to 0. Then it's an ideal sheaf. But yeah, otherwise I have to tensor. I have to fix the determinant otherwise. But we'll go through something similar somehow. Yeah. Thanks. Yeah. Okay, so good. So, okay, so what I want to do now, I cancel here, yes. Okay, so let's see now the positivity. So the next thing I have to do is that, okay, I know when this guy is stable, now I want to associate a divisor to this guy. So how do I do? We took this definition from it's actually a general definition somehow. This is true in any dimension, in any blah. So how does it go? It goes as follows. So I take sigma stability condition on anything, but let's say on X at the moment, whatever. And I'm fixing some numerical class. Okay. And then if I take a proper scheme, so what I do the following. I also look at a family E in VB X cross T, as usual, such that this guy is a family of semi-stable sheaves. So E restricted to any point T is in A and is sigma semi-stable. Okay, and I'm also assuming that the churn character, or better, the v of et is just my fixed v. Okay, so it's a family of semi-stable sheaves parameterized by a scheme T. And now I can define a divisor class on this. Of course, I will want to apply this theorem, this lemma actually, on the case in which T is the Hilbert scheme. Okay, so that's the only thing I need at this moment. But it's actually a more general result. So I define a class. It can only be defined as a class that I call L depends on E and depends on sigma. So this element is an element in the Néron Severi of T with real coefficients. And so what it is defined as follows. I start with an integral curve. And so what I do, I just define L by smashing it with a curve. And the thing is I define the following. So I define L of V comma sigma times C. So this is defined as follows. So this is defined by negative the imaginary part of Z applied to the following things. So this is Q lower star E tensor P pullback of the structure sheaf of C divided by the Z of V. So let me say briefly what this means. Again, I have P and Q as before. You can imagine what are they. So P is the projection onto X, and Q is the, opposite. Q is the projection onto, so I have X cross T. I have the projection into X and the projection into P. T is any family, yes. So E is any family, not universal a priori, yeah. Then after I will apply with universal family, of course. Yeah, but this is a general thing. So it's any family on a proper scheme. I give this definition. So this defines a divisor, right? Because I define how this guy intersects with all integral curves. Okay, so that's the finite divisor. Why? So here I'm taking the structure sheaf of the curve, I'm pulling it back to the product, tensoring with E, all derived, and then take push forward. So this guy is an element in X, and then I apply my Z. So this is well defined. So this is a complex number. I take the imaginary part, I take the minus sign. And once I define it on curve, I can extend by linearity and give me a class. And now the lemma is the following. And this is useful for a lot of things, actually. So this is R and Bayer. This is the only result that we use here, is that this class is Neff. Oh, E sigma, I call it. Okay, so that's how to associate to any stability an F class on the moduli space, essentially. And you can say more, and that's the second part, which is interesting. So the moreover is that I can say exactly when f ends that C is 0, it's exactly what you expect. So it's going to be 0 if and only if it parameterizes a family of S-equivalent objects. Moreover, I know that L dot C is equal to 0 if and only if I have the following property, that for generic points C and C prime in C, I can say that E restricted to C and E restricted to C prime are S equivalent. So this is a standard result in some sense, but here we're going to apply by varying stability. So somehow we have this family until we hit a wall, and the family parameterized before is going to be a family of semi-stable objects there. And so, okay, so that's the lemma that I want to use. Oh, wow, I'm late. Okay, the interesting thing about this lemma is that it follows from Abramovich-Polishuk. But maybe, since I'm out of time, maybe let me just say briefly how's the idea, maybe, just the idea of the proof. And then it's done. Once this lemma is written, then it's just a check of what's going to happen. So how to prove this lemma? At least an idea of the proof. But the following thing happens. First of all, I can reduce this is not super important. It's just by rotation. I can reduce to the following two conditions: that Z of V is -1, and the category A is Noetherian. So I can actually apply Abramovich-Polishuk. Okay, and that's not so hard. And then what happens? Happens the following thing. So what is my divisor on a curve? So L dot C, in this assumption, this becomes just the imaginary part of Z, so it's my rank. So this is nothing but the rank of the following objects. So it's just the Q lower star of E restricted to X cross C. That's the only thing I'm looking at now. Where R is the rank associated to sigma. Okay. And now it's easy because somehow now the only thing I need to check that this guy is in the category. So this is not true, but I can use Abramovich-Polishuk. Will not be in the category, will be in the category once I tensor enough times with C. So let me say briefly. Now, E restricted to C is in the category A for all C in C. That's by assumption. And so this implies, by the property I told you this morning, that E as a family is in the Abramovich-Polishuk category AC. Okay, so that's the thing. But now I use that the definition. So this implies that if I choose OC of n, OC of 1 ample, I can choose anything I want, then it shows that Q lower star of E restricted to X cross C tensor OC of M is going to be in the category for all M large. Okay, so that's the definition. But now it's not so hard to prove that if I tensor by M, essentially I'm just changing the rank by 0, just changing the real part. So this guy, this is very easy to compute, is just the rank of the same thing, but with tensoring by O of n. Now this guy is in the category, so it's positive. By definition. Okay, so it's very simple, this part. But we are using Abramovich-Polishuk category. And it's the proof that this thing is a bit more annoying, actually. But you have to carefully analyze stability to prove the second part, which actually we're going to use. Okay, but that's the positivity. So we associate to any. So essentially what we do the following thing. We have a map from the space of stability conditions or better, to our alpha beta plane, to the Neff cone of our Hilbert scheme, or in general to any moduli space. So then I have a map L, now for us, by taking T equal to the Hilbert scheme and E as the universal family, better the idea of the universal family. So what I define a map L, which depends on sigma alpha beta, from a subset of the space of stability conditions into the Neff cone of Xn. Okay? And so I just have to compute a class now, but that's very easy. That's elementary thing to do, just a computation. So I can compute directly the class. So let me say another lemma. I think this is the third lemma that we saw today, now. It says that I compute L, so I of sigma and then sigma alpha beta. It's equal to, I just computed, and that's precisely what you might expect. So it's equal to negative E divided by 2 plus 1 plus alpha square divided by 2, d plus 2n divided by 2d h plus kx divided by 2. Okay, so that's a computation. That's required nothing. And let me see what happens. So if alpha in particular, for alpha going to infinity, what do I get? I get everything disappears except h. So L tend to h. And if alpha goes to 0, whenever I have beta equal to -1, this guy, what is going to do is going to give me, this is minus 1. Sorry. And so this guy is going to tell me that L tends to the divisor that we know, right? The one I wanted. So, D that appears in the theorem. And so that's give you the first part of the theorem automatically, right? So I know exactly that these guys are all Neff. And so that's proof the first part of the proposition that we said. Sure, yeah. Sure.
I mean, you're using the S equivalence.
Now I'm going to use it.
I mean, the moduli space, you take the classes of S
Yeah.
equivalence. So in all these, I mean, when you're considering this family,
Mm-hmm.
you are like splitting these points. I mean, the point in the moduli of slope of mu.
Yeah, it's slope stable. Yeah.
Identified
No, here,
equivalent.
but here they are all stable. They are.
Here, I mean, in the moduli of mu stable bundles, you are identifying the S equivalence bundles.
In general, you mean?
So here you are splitting them.
Uh,
Families.
Yeah. No. Yeah, you mean you have to be careful. Somehow. The way in which I'm using this theorem is slightly different. So I'm not going to apply it to the family, which is the universal family of the moduli space. I'm going to apply to something which is before the boundary. You're going to see some of this part.
Yeah,
So I'm not going to apply to the moduli space directly.
Yeah, but I mean, it seems to me that you are taking something like the singularization in some sense. And for each S equivalence classes,
Yeah.
in the previous moduli space, you have the family with all the elements.
That's correct. Yeah. That's fine. Yeah. So this guy is going to be.
But in the limit,
They're going to get.
all these are defined in just one point.
Ooh,
Because they are S equivalent, so
Mm.
they define just one point in the moduli.
Yeah, in the moduli space, yes, but I'm going to apply it slightly differently later. Yeah, you'll see that. You will see now how I'm applying it. So you're right, somehow. This guy is going to be something. This condition, you have to be careful how I apply this condition. So here, I'm applying this condition only for this moduli space of stable objects, right? So they're all stable, right, by the lemma. So here there is no S equivalence at the moment. It's just positive on all curves, right? Now I'm going to apply it. Let me write actually. Yes, it's easier actually. So I can. Let me see if I can try to say how to do this. So how am I going to apply this thing? I'm going to apply as follows. So now I have my family in my alpha beta plane. And I have my -1 here, and I know that here there is nothing, so it's always stable. Okay, so the theorem applies in a family of Neff divisors. So this proves the part one of proposition. So let me say this thing. Okay, so this proves proposition, the first part. So the interesting thing is to see the second part. I want to see where the boundary is. And so how do I do this? So now I'm looking at the wall. So I'm just moving slightly here. And then I'm doing the same thing. Okay? So I'm taking beta to be -1 and -epsilon, for epsilon small. Okay? And now what is the trick? The trick is that I'm moving again for alpha goes to 0. Okay? And so what is the trick here? The trick is the following. So I take this beta in this form, and then the statement is actually very simple. It says that then there is an alpha, so let me call it beta 0. Alpha 0, which is positive, such that the following thing happens. So I gamma is sigma alpha beta 0 stable for all alpha greater than alpha 0, and I gamma is sigma alpha 0 beta 0 semi-stable at alpha 0. Okay, so what I'm doing, essentially, there is a wall here coming out, and then I'm going down until I hit this wall. Okay, and so what I know also, so let me finish the statement, and I also know that and the slope at alpha 0 beta 0 of O minus H is the same as the slope alpha 0 beta 0 of my ideal shift gamma. So this is exactly the point where It's stable all the way, and maybe semi-stable, but maybe not stable. So I just have to find when it's not stable. And now here's the key. So how do I go now? The following. Sure. There is this alpha for which this happens. For all of gamma. Somehow they are all stable above, and at a certain moment they might become semi-stable. Maybe. Yeah, they cross the wall. That's correct. Yeah. Maybe all, maybe one. We don't know yet.
So there is one. Otherwise,
we'll see now. Yeah, we'll see now. We'll see. So a priori at the moment it's fine, right? Might be semi-stable instead of properly semi-stable. So how does it depend? So this depends by the following things. So I have a map from 0 goes into O minus H, goes into I gamma. Okay. So if there is a map, which means as following, if the points lie on a curve inside the linear system, then this guy is going to get destabilized. Because this guy is stable everywhere, by what we saw today. Okay, so those are the ones that might become unstable. Okay. No, they will become unstable at this wall, semi-stable at least, because the slope is the same. Okay, so you have a map from one to the other, which is an injective map. Okay, and so I take the quotient, which is whatever it is, or C minus gamma, and here you see what happens. Where C is just a curve inside H, and this thing happens if gamma is contained in C. Okay, so I have all stable here. I hit this wall. The one which are inside a curve inside the linear system H, they become semi-stable. When I cross the wall, becomes unstable. Okay, so that's the idea that we have here. So we have a wall, so it's great. So now what I'm looking at a family, but the family E that I'm taking is still the same family as before. So it's the family IC. Right. So now I'm looking at the divisor, which is, what time is it? Okay. Now here's the trick. So this guy is a short exact sequence in co B0x. Okay. And so what I'm doing, I'm looking at, and so here is what I'm saying. So I'm looking at L, but still the same ideal. Sigma alpha 0 beta 0. Okay. So this is a family of semi-stable objects now on sigma alpha 0 beta 0. So this guy is telling you exactly what happens. He's going to contract a curve if and only if I have a family of objects which have the same S-equivalence class. But now you see how it works, right? Because if I have a curve C with a G1n, this guy has, there is a P1, right? So that's the trick here. So, and that's exactly the condition for having, so if C has a G1n, then take the corresponding points in C, and so what do I get? Well, I get a P1 of S equivalent I gamma, right? Because I smash them into a sequence where this guy is constant and this guy is constant, and there is a P1 of them, of extensions. And so what do I get?
That's the curve which is being contracted.
It is the curve which is being contracted. And so, and then I get at L, the same L, dot this curve gamma is equal to 0. And so it's actually the boundary of the Neff cone because it's not ample. Okay, so that's how to use this L to describe Neff cones of Hilbert schemes. So if you have a control when a G1n exists, then you get something. And vice versa, if for some reason you can prove that a certain wall corresponds to an actual wall in the sense that it contracts something, in the sense that there is a family of S-equivalence objects, then I get a boundary in the NF cone. Okay, so that's the idea somehow of the. Okay, I have 5 minutes left. Yeah, so this is, I want to say maybe one more thing, I guess not threefold. So of course this thing for general type, for this surface in general, you don't know much. Somehow you know when sometimes this thing exists, of course. But then the interesting thing is that what next? So I hit the boundary of the NF cone, can I go further? So can I study, is there a flip after? Is it the same? And so how do I do this? This is you cannot do in general, but you can do for K3 surfaces. So let me just maybe make one final remark.
In this case, you can describe what is inside the circle?
Yeah, we don't know actually. We don't know somehow. In general, it's complicated. Somehow, once you cross the circle, sometimes you're lucky, and so you get really a birational map. And so since you have a divisor doing this thing, it's going to be a flip. And or for a flop, whatever happens, or maybe a divisorial contraction, that could happen also. But if you're unlucky, especially if this happens in general type, there is no way to expect that you get something nice. So probably you cross the wall and you get maybe a P1 bundle over your space, or you get some moduli space which have several components, even if you start with the Hilbert scheme. So unfortunately, in general, you have no control of these things.
But you still have this class.
You still have the class, yeah, you still have the class. But maybe somehow.
All those are projective at least.
You don't really know, right? Unfortunately. Because this L is the most positive as you can imagine, but it's not enough to prove that it's projective. So for proving that it's projective, you'll need to prove that once you cross the wall, the neurons keep the same dimension, for example. And so you don't know that, unfortunately. But you know for K3 surfaces. Okay, so example, which is not so. So okay, I have 1 minute. I guess somehow you can cross the wall and get a birational transformation. And so what happens? You get all of them until you hit the last part. So essentially, what you do, you describe completely the movable cone for the Hilbert scheme of points on any K3 surface, actually. And how do you do? You just apply the same argument over and over. And the only thing you have to work a bit harder actually, is that you have to prove that a wall corresponds to a wall in the NF cone. Unfortunately, this is not true, but still, you can control the one where it doesn't happen. So somehow, it could happen that everything becomes unstable. You cross the wall, but still, these guys still remain ample, because they don't even contract anything. But anyway, the problem that you prove that L gives a map from the space of stability condition, the whole space actually in this case, into the Néron-Severi group, for example, of the Hilbert scheme, but in general of any moduli space. And the thing that you can prove is the following, is that the image of the map L is actually contained in the closure of the movable cone. And you can prove that every birational model, which is also K-trivial of this guy, it's going to appear as a moduli space. And you can describe also what happens at the boundary. So whenever you expect that something is semi-ample, it's going to be semi-ample. Okay, so it's a bit stronger version. So this guy essentially, whenever the Mori cone the cone is finitely generated, is a Mordani space, for example. You get it just by computing all birational models. And then you can use this to prove many conjectures about these spaces. Like you can generalize a good way some of the conjecture of Hassen-Chinkel. You can prove some sort of abundance conjecture. You can prove Kawamata-Morrison cone conjecture, and you can deform and prove it for every hyperkähler, which is the formation equivalent to these spaces.
That is relating the stratifications? Or
Sorry?
that is studying the stratifications of the Néron-Severi?
That's correct, yeah. It's telling you that somehow if I have a wall here will correspond to a wall here. But not vice versa. So here you have more walls, but you can control them. Yeah, so that's the whole argument, but requires a bit of work somehow. Yeah, and you can describe explicitly the movable cone or the NF cone in terms of purely numerically somehow. Yeah. Sorry, that was a bit fast actually. Okay, sorry, I'm done actually. Thanks.